Okay, welcome to the second lecture in Math E102. The students in the room are being told that they should drop their homework off here, and I will take it to Chris to be graded. The first homework assignment to came in by email from Iraq yesterday, and when I looked in the email box, we had 3 homeworks there at 6:30, and I assume that a bunch of others have come in on the fax machine. So we will collect these, get them graded, and if there's no indication to the contrary, I will just bring the homework to class next week, and you can collect the graded problem sets there. Or if you come to section, you can probably pick them up from Chris. Anyone who's here watch any or all of the first lecture online? Okay. Any useful tips for me? Or for the cameraman?
No,
okay. I looked at it. It's always very embarrassing to look at oneself on video, but I was reasonably comfortable with what I saw, and at least the 5 or 10 minutes I looked at, the camera work on the whiteboard seemed to be perfectly good enough to read everything. So if anyone has occasion to dip into these online and wants to offer me feedback, that would be most useful. Okay, following general principles of teaching, I'm going to start off with just enough of a review so that someone who missed last week will have a vague idea of what I'm talking about, and that means I'm going to start with topic number 1 in the outline called Review of the Basics, and summarize what an event space is and what a probability function is, which you already were introduced to last week. So this will hit all the highlights. The things that we assign probabilities to are event spaces, and the hard part about an event space is making a fancy-looking letter to represent it. That's my attempt at a fancy-looking F. And here are the properties that an event space has to have. The universal event has to be in the event space. And the reason for that you now know. One of our axioms for a probability function will assign a probability of 1 to this event. And if this event is not something we can assign a probability to, that doesn't make much sense. If an event A is in the event space, for example, going back to murder mysteries, the murder was committed by the butler, then its complement also has to be in the event space. The murder was committed by someone other than the butler. And finally, this is the fancy version, but it's the one we need. If we have a bunch of events, I'll index them with an integer j. So if we have a bunch of events that are all in the event space F, for j equals 1, 2, 3, and I'm going to put ... but this means we may have a finite number of them, we may have a countably infinite number of them, and the requirement is then the union of all those events up to n or infinity is also in the event space. And it might strike you as a bit far-fetched to be talking about infinity. You might think, infinity's fine for mathematicians, but in real life, there's only a finite number of events. I'll devote about the last third of this lecture to perfectly reasonable problems where the fact that this runs up to infinity is crucial in analyzing the problem. So this is all we require of an event space, but we can prove a little bit more. I proved these things last week. The null event is in the event space. It will have a probability of 0, but we need it there so we can talk about it. And if we have two events that are in our event space F, then we can also show, and I did show this last week, that the intersection of the two events is in the event space, and the difference of the two events, the first event take away the second event, is also in the event space. And let me give you just one new one. This is also in the event space. Mathematicians call it the symmetric difference. Computer folks would like to think of it as exclusive OR. It's the same concept. And the notation that our textbook uses for it is A little triangle B. This is the set of events that are in A or in B, but not. It's the set of individual outcomes, set of points in a Venn diagram, that are in A or in B, but not in both of them. That's what makes it an exclusive OR. So if this is A and this is B, we're talking about that with this little piece left out. Okay. Who can see the obvious proof that this is in the event space?
It's the complement of the intersection.
No, it's not the complement of the intersection, because
Right.
there's all this stuff out here too. In order to show that this is in the event space, you have to show that you can make it out of two things that are guaranteed to be in the event space by using operations under which the event space is closed. Yes?
I just wanted to point out actually that the level of the Venn diagram is just inching below the lectern, so
Thank
that for
you.
people on this
Okay.
side. Thank you.
That's like raising a point of order, and it always gets priority. Thank you. Okay, so here's a Venn diagram that you can see. Can someone see how to describe this event in terms of events and operations? Yes, Robert?
Okay, A union B, which is all your greenies, and the stuff in the middle, intersected with the complement of A intersect B.
That's correct, but you can make it a little more concise and elegant. That's absolutely right, but there's a cleaner way of saying it. Anna?
Take the difference with A intersect B.
Yeah. So either way is fine, because last week you saw that you can write differences in terms of unions and complements. So it's A union B with A intersect B removed from it. Okay, so there's our event space, and now I will clean this off, and I guess that's about the right lower limit. We've got these slightly. That help a little bit? Okay. Now I have to review probability functions. We can get into some new stuff. So, for a probability function, which we write with a fancy P, we make the following assumption. The value of this probability function can never be negative. So if an event A is in the event space, its probability is either 0 or positive. And if it's not in the event space, the probability function just isn't defined. You could read what I said as saying if it's not in the event space, it could have a negative probability, but it can't even have a defined probability if it's not in the event space. The probability that something happens is 1, and that implies that the probability of the null event is 0. And finally, this is the crucial one, the probability of a disjoint union of events is the sum of the probabilities of those individual events. So we take the union from j equals 1 to infinity of a set of events called a sub j, and that's equal to the sum from j equals 1 to infinity of the probability of the individual events, provided these events have what property?
Disjoint.
They have to be disjoint. So this is true only if AI intersect AJ is the null event for all pairs I and J. And basically, that's all there is to probability theory. We're going to be working out the consequences of these assumptions about event spaces and probability functions. I want to start with topic 2 now, which is DeMorgan's laws. And I want to preface this with a brief reading from the admission requirements to the master's program in the extension school. This is the version that now appears in the catalog. And it's correct. Students whose native language is not English and who have not completed a 4-year bachelor's degree in an English language curriculum must take the TOEFL. You got that? Students whose native language is not English and who have not completed a 4-year bachelor's degree. Well, a couple of years ago, these rules came up to the ad board for approval, and it had an or rather than an and in it. And I said, that's wrong. We should amend this. We should change or to and. And someone on the committee said, no, that's right. And I said, no, you don't understand DeMorgan's laws. So I had to explain DeMorgan's laws to various members of the ad board who represent a variety of disciplines from classics to archaeology. And let me write these down for 2 events and then show you how this applies. So there are 2 of these DeMorgan's laws. They're surprisingly simple to have a name attached to them, but they do. So the first one says, if you've got the union of 2 events and you take its complement, you get the intersection of the complements. And this is the surprise. It's basically changing or to and. And the second one is very similar. It says if you take the complement of the intersection of 2 events, that's the same thing as the union of the complement. So the rule is if you pull the complement inside, you have to switch intersection to union or vice versa. Okay, so let's look at this in the context of pure logic. Event A is non-native. Event B is non-English degree. And the complements of these, A complement is native speaker of English. B complement is English degree. And while this was, yes, Jay?
I don't think that's what it said, is it? It just says 4-year degree. It doesn't say anything about English.
I'll read it again.
Oh.
Students whose native language is not English and who have not completed a 4-year bachelor's degree in an English language curriculum. So what I mean by English degree is completed a 4 years bachelor's degree in an English language curriculum. Now, this was not stated in probabilistic terms, but we could say the event is we pick a master's applicant at random, and then event A could be the person we pick is a non-native speaker of English. Event B is a non-English degree. And event C, which is must pass the TOEFL, according to the rule as it mistakenly got to the ad board when it said students whose native language is not English or who have not completed a 4-year bachelor's degree would have been what? Students whose native language is not English or who have not completed a 4 years bachelor's degree in an English language curriculum. Describe that one as an event in terms of A, B, etc. That would be A union B, wouldn't it? And C complement, exempt, is what, according to DeMorgan's law?
Complement of
A complement and, or intersect, B complement. So here's what actually happened. I said, you know, my son-in-law was born and raised in New York City, but he went off to Greece to university after dropping out of high school, and he got a bachelor's degree on the basis of 4 years of study in Greek in Athens, and he's taught for us in the summer school. Are you saying that he has to take the TOEFL? And whatever official was responding to this said, no, no, no. If he's either a native speaker or has his degree in a 4-year English language curriculum, he's exempt. And that's why we put or in the rule, to which I replied, of course, you don't understand DeMorgan's laws. When you have an or in the rule and you complement things, you have to change the or to and if you want an or in the exempt, which is right, if you're either a native speaker of English or if you did a 4-year bachelor's degree in an English language program, you're exempt, then you have to put and in the rule. And if you go online and look at the rules, you'll discover the correct and is now in there. So this may look trivial, but full professors from time to time run afoul of it. Not full professors of mathematics, I trust. What I'm interested in doing, though, is extending these principles from 2 events to n events. And this is going to be the first of 3 inductive proofs for the evening. One of the goals of this course is to make you all thoroughly comfortable with doing inductive proofs, because this is one of the great ideas and great skills in mathematics. So let's try extending this. To do an inductive proof, you need a base case and an inductive step, and the base case that I'm going to use here is one of the DeMorgan's laws, that A union B, when you complement it, gives you A complement intersect B complement. Now, what I need to do is to prove that the principle is true for n plus 1 if I assume that it's true for n. Alternatively, I could assume that it's true for n minus 1 and prove that it's true for n. I'll do that later on. That's a matter of just making the indices look neat. And in this particular case, I like it this way better. So I'm going to say what I'm interested in is knowing the complement of the union of A1 union A2 union on up through AN union AN plus 1. What I'd like to do is show that a similar formula holds for this. And the standard idea in these elementary proofs is almost always you reduce the n plus 1 case to the 2 case by putting in some extra parentheses. So I can regard this as the union of two events. And since it's the complement of the union of two events, I can use DeMorgan's law and say this is A1 complement. Well, I'll do it in 2 steps. I can say this is the complement of the first event, A1 union A2 on up through AN, complemented, intersect the complement of the other one. And now here's the step that upsets people who are not yet thoroughly familiar with inductive proofs. I'm going to say I'm entitled to assume that the result is true for case n. So I can write this as A1 complement intersect A2 complement intersect A3 complement intersect dot 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 AN complement intersect AN plus 1 complement. And I have shown the result for n plus 1 on the basis of the assumption that the result is true for n. And the basic argument underlying this, I remind you, is we know that it's true for 2. This then shows if it's true for 2, it's true for 3. If it's true for 3, it's true for 4, and so on. And therefore, it is true for any arbitrary finite value of n. I don't think I'll take the time to do the corresponding proof for the other DeMorgan's law. Might make a good quiz problem. Instead, I want to do a little application to a game called Chuck-a-Luck, which actually took me in to my great embarrassment when I was a teenager. So can we have a look at this camera? Ah, there we go. Okay. So this is a game that is played at carnivals to separate fools from their money. The way it works is this. You pick a lucky number. Say I pick my lucky number is 6. I then put up $1, and 3 dice are rolled. If a 6 shows up, I get $2 back. If no 6 shows up, I lose my money. And my reaction to this as a very naive high school student was, well, this looks like a fair game and it looks like fun. I'll play it for a while. And a few dollars poorer, I realize the error of my ways. The odds are very strongly in favor of the person running the game. And I now want to explain why that is so. So let me just make sure everyone understands the rules. There I get $2 back. And really, this is the catch in the game. I rolled 2 6s, but the carnival barker says, oh yeah, you got a 6. You win. You get $2 back for your 1. And what I want to show you now is that the probability of rolling at least 1 6 is significantly less than 1/2. And I'm going to do this in the shortest way by applying the DeMorgan's law that I just proved in general to the case of 3 events. So A1 will be the event a 6 shows on die number 1. And the same thing is true for die 2 and die 3. The probability that I will win the game is therefore the probability of what event?
A1 or A2 or A3.
A1 union A2 union A3. Saying or is okay, but union is the standard event terminology. So if the event A1 union A2 union A3 occurs, then I win the game. Now, here is an easy way to calculate this. I can say that the probability that this occurs is 1 minus the probability that its complement occurs. Everyone comfortable with that? And by DeMorgan's law, this is the probability of A1 complement intersect A2 complement intersect A3 complement. What's the probability of A1 complement? 5/6. The probability of A2 complement is also 5/6. The probability of A3 complement is 5/6. So this is 1 minus 125 over 216, which is 91 over 216. So I have considerably less than a 50% chance of winning this game. And of course, you don't need any fancy stuff to convince someone that this is true. You just say, hey, look, consider this first die. What's the probability that it's not going to have a 6? 5/6. Same for the second, same for the third. The probability that all three of them will fail to show a 6 is therefore 5/6 cubed. Okay, I'm now ready to move on to topic 3, inclusion-exclusion. And I want to review the result I proved last week and then show you how, by induction natch, to extend it to more than 2 events. And then I want to show you that this works also for analyzing Chuck-a-Luck. It gets you the same right answer in a slightly more complicated way. So here's what I proved last week. The probability of the union of 2 events, not necessarily disjoint now, is equal to the probability of the first plus the probability of the second minus the probability of their intersection. And now I'm going to use this as my base case for induction, but because this gets rather tedious to write out in detail for the case where we have n events, I'm only going to do out the calculation to show that we can go from 2 events to 3 events. Once I've done that, I think it will be fairly obvious how to go to n events, and I will just state the general result. So what I'm interested in is the probability of the union of 3 events. That is, after all, what we were concerned with Chuck-a-Luck. And anyone having seen what I just did with DeMorgan's law want to suggest what I should do to this operation in order to be able to make progress with it?
Rewrite it in copy.
This is what I've got to work with. How can I rewrite this so I can apply this as a tool to that?
Combined A1.
Right, definitely.
Suggestion?
Combined A1 and A2.
Combine A1 and A2. Absolutely right. So I'll slap in some extra parentheses here. And now I've got the union of 2 events, don't I? I have the probability of A1 union A2 plus the probability of A3 minus the probability of A1 union A2 intersect A3. Okay, now we're making real progress because now I can apply the 2 event case to get probability of A1 plus probability of A2 minus the probability of A1 intersect A2. Then I've got the probability of A3, and I have to subtract off a probability involving this event. Now, I can't do anything with this as it stands, but I can rewrite this as a union of 2 events. Can anyone see how to rewrite this as a union of 2 events? Yeah, Jerry?
A1 intersect A3 union A2 intersect A3.
Yeah. Okay, so now I've got this as a union of 2 events, and this turns into minus the probability of A1 intersect A3 A3 minus the probability of A2 intersect A3. Finally, one last term plus the probability of A1 intersect A3 intersect A2 intersect A3. Yuck. Who can see a simpler way of writing that?
A1, A2.
If A1 and A2 both happen, and A1 and A2 and A3 both happen, what's a simpler way of expressing that?
A1, A2.
A1, A2, and A3 all happen. So my final result, when I combine the terms, is the probability of A1 plus the probability of A2 plus the probability of A3 minus the probability of A1 intersect A2 minus the probability of A1 intersect A3 minus the probability of A2 intersect A3 plus the probability of A1 intersect A2 intersect A3. And the general case of this, which I can write down, is if you have a union of lots of events, the probability of A1 union A2 up through A n is equal to the sum of the probabilities of the individual events minus the sum of all the probability of intersections of pairs of these events where I is going to be less than j, which is going to be less than or equal to n, plus the sum of the probability of triples of these events intersected, the probability of ai intersect aj intersect ak, where I is less than j, is less than k, less than or equal to n, minus dot, dot, dot. It goes on forever, and I think I put on the homework to indicate how you can prove it by induction. That's left as an exercise in the book. Now, let's apply this to Chocolat. You might look at this and say, this is so complicated that I don't think it would really be very useful in practice. But in fact, it's remarkably useful, and the reason it's remarkably useful is that it's kind of counterintuitive. There's no really simple explanation of this. You can't explain the minus sign, why you go subtracting probabilities. So this is a slightly subtle result in this case, and it gives you correct answers in a way where you can't really assign individual meanings to the numbers that you're adding up. Yes, Jerry?
Doesn't it help to think that you have to avoid double counting the things that are common to both events?
Yes, that's the idea. It's avoiding double counting, and in the 3-event case, the Venn diagram looks like this, and this is the last term where in avoiding double counting you subtracted something too many times and you have to add it back in. You can probably talk your way through this one, but once you have more than 3 events, it's almost impossible to visualize this in terms of Venn diagrams, and you have to fall back on the inductive proof. But let's try this out on Chocolat. So I will erase the top here. Yeah. So here's the formula I'm going to apply. I'm going to be daring. I'm going to switch to a different color. Please let me know if this is hard to see, but I think the board is turning so gray that red may stand out better. So for Chocolat, probability of A1, the probability that when I roll the first of these dice, it comes up a 6. 1/6. That was easy, wasn't it? Probability of the representative event A1 intersect A2. I roll my first 2 dice, and they both come up 6s. What's the probability of that event? 1/36. And finally, the probability of A1 intersect A2 intersect A3, where I get 3 sixes, is 1 over 216. Now you can see this messy looking sum down here is going to be very easy because no matter what events you choose to intersect, the probability is the same. So we just have to multiply by how many there are. So the probability of A1 union A2 union A3 is going to be how many times 1/6? 3, because there are 3 dice. Minus how many times 1/36? Because there are how many pairs of dice are there? 3. Plus how many times 1 over 216? 1, because there's only one triple. So this gives us 108 over 216 minus 18 over 216 plus 1 over 216. And again, we get 91 over 216 by a different sort of calculation. Any questions about this? Okay, we're going to go on to cups and saucers now. These are a couple of very nice examples from the book. And here's the theme for the rest of the evening. I'm going to be doing probability problems where you can get the right answer just by organized counting, but the organized counting will not involve the use of binomial coefficients. We'll do lots and lots of examples with binomial coefficients next week. This is going to be sort of ad hoc, roll-you-around counting. And what will make it tricky is you have to find a situation where it's a reasonable assumption that all the individual outcomes are equally likely. So that's one theme we're going to have. Another theme is going to be continuing to use inclusion-exclusion to help us out in doing this. And the third and final theme will be cases where we have an infinite number of events. But I'm going to start out with cups and saucers. So here we have 2 red saucers and 2 blue saucers. And I'd like you to arrange these in a random order. I won't look. Okay, I'll take them from you, and I'll plop them down, and I plop them down 1, 2, 3, 4. Now, the first question I want to ask is, if you closed your eyes and we did this again, and you then opened your eyes, what is your estimate of the probability of red cup number 2, which has the 2 strips of tape on it, being on a red saucer? 1/2, right. Wasn't said aloud, but it was correct. So for either of the red cups, the probability that if my assistant shuffles them and I lay them out on the saucers, that an individual red cup ends up on a red saucer is 1/2. With that in mind, I can do this problem using inclusion-exclusion, and then I will do it by a slightly different technique, which is very similar to the one used in the textbook. So, my assumption is that all 4 factorial, that's 24, permutations are equally likely. And,
Oh, it's almost invisible.
okay, we'll give up on green. Well, I'll read it. So the assumption is that when my assistant, who can't go on camera unless you've submitted a form, when he shuffles these things, these are 4 distinguishable cups, and any order has a probability of 1/24 of showing up. So this is a safe assumption in many cases about equally likely individual outcomes. And what I want to calculate is what is the probability of the event at least one cup is on a saucer of the same color. They're not all wrong. First thing we have to do is take that event described in words and express it in terms of symbols. And it's worth noting, if a red is correct, then a blue is correct. That is to say, if somehow or another one red cup gets plopped down on a red saucer, there's no way to put both blue cups on red saucers because there's only one red saucer left empty. So that means we just have to calculate the following probability. If R1 equals red number 1 on a red saucer, and event R2 is red cup number 2 is on a red saucer, what we have to calculate is the probability of what combination of those two events? The union. It has to be the union, doesn't it? Because I've just been talking about inclusion-exclusion, so I have a formula for dealing with this. So we want to calculate the probability of R1 union R2. Now this is really pretty easy to do. You shut your eyes, we reshuffle the saucers and cups, you look at them, what's the probability that red cup number 1 is going to have been plopped down on a red saucer? 1/2, right? Because there are 2 red saucers and there are 2 blue saucers, and don't worry about, well, I don't know what happened to the other ones. If you open your eyes and focus your attention on this cup, it's got a 50% chance of being on a red saucer. Likewise, this one has a 50% chance of being on a red saucer. So P of R1 equals P of R2 equals 1/2. What's the probability of the intersection of these two events? Well, that's a little bit trickier, though not as hard as the dealing 2 spades problem I did last week. You got 1 chance in 2 that this one gets plopped down on a red saucer. Okay. Now I walk over to my assistant, grab the second one, and I plop it down at random. What's the probability I'll plop it down on a red rather than a blue saucer? 1 in 3. So the probability of that intersection is 1/6. And finally, by inclusion-exclusion, the probability of the event R1 union R2 is 1/2 for R1 plus 1/2 for R2 minus 1/6 for the intersection, or 5/6. So that's one systematic way of getting the answer. Another systematic way of getting the answer, which is described in the textbook, is called making the sample space smaller. And here's the way this argument works. Rest assured, I have brought my spray bottle of whiteboard cleaner, so we'll have this nice and clean after break time. But I think we can live with it for the moment. So here's a smaller sample space. Don't fuss about red cup number 1 and red cup number 2, blue cup number 1, blue cup number 2. There are basically 6 ways that the colors can be distributed. RRBB, RB, 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 B, R, B, R, R, B, B, R, B, R, and B, B, R, R. So these are red saucers here and blue saucers here. And if you accept that these 6 alternatives are all equally likely, these all have at least one red correct, and only in this case is every cup on a saucer of the wrong color, and therefore there are 5 chances in 6 that you get at least one red correct. That's great. Now, who would like to give an argument, for example, that this outcome is precisely as likely as that outcome? Remember, we can take it for granted that all the permutations of the 4 cups are equally likely. So if we go to individual outcomes, which are the 24 different permutations, we can assume those are all equally likely. Given that, why would you say this one is as likely as that one? Yeah,
you
Jerry?
can permute the 2 reds and the 2 blues without making any difference.
Very good. Okay, so if you have one way of setting up the cups that comes out R, R, B, B, you can get 3 more from it by interchanging the red cups and interchanging the blue cups. And therefore, each of the outcomes in this smaller sample space is a combination of 4 of the individual outcomes that we've agreed are equally likely. As long as we've agreed that all the 24 permutations are equally likely, all we have to do is note that each of these is the union of 4 of those, and we can say all of these are equally likely. That's a step that's easy to overlook, but very soon I'll be showing you a couple of problems where we have a sample space where the events are not at all equally likely, and the art lies in starting with some equally likely outcomes and working to probabilities for the outcomes that are not equally likely. Okay, I think I can sneak one more example in before we take our break. So I'm going to do number 5 now, which is cups and saucers number 2 with 4 colors. Now, Tommy's convenience store does not sell green cups, so that will have to do for green. So this time we got 4 saucers. Red, blue, green, and yellow. And 4 cups of 4 different colors. And what we'll do now is you hand them to me in a random order. So hand me one, I'll plop it down. Another one. Another one. Another one. And 2 of them came out right. What we need is a randomizing Dixie cup dispenser, which is engineered to make all the permutations equally likely. Incidentally, one reason that playing cards are so good for games of chance is that there's this simple mechanical operation of shuffling, which, if repeated 7 or 8 times, really leads to a situation where all the 52 factorial permutations of the decks of cards have pretty much the same probability, even if the cards were arranged in order to start with. Okay, so here's the question in cup and saucers number 2. If we do this, we put the 4 saucers down, permute the 4 cups at random and plop them down, what's the probability that at least 1 cup shows up on a saucer of the same color? And I want to show you that the answer is 5/8. How do you get a 5 out of this when there are 4 cups? Well, if you think a 5 is strange, the last problem I'm going to do tonight, the probability turns out to be 300 1,001st. It's very hard to imagine a problem that has a 1,001 in its correct answer. Okay, let's define one representative event for this case. Event R is the red cup lands on a red saucer. And I will define B, G, and Y similarly. So what event are we interested in?
Or union B, etc.
R union B, etc. Thank you, Jay. R union B, union G, union Y. Everyone see that? This is a union of these four events. So if any one of the four cups hits the saucer of the same color, we win. Now, this one is really hard to do in general, but it's very easy to do by inclusion-exclusion. So this will be an example of that messy-looking inclusion-exclusion formula that I wrote down for n events, but applied with 4 events. And I'm going to do it by a slightly shortcut technique. Once we have the probability of the event R, by what factor do we multiply in order to take into account the fact that we should be summing the probability of all these events taken one at a time? 4. Okay. The next term has a plus sign or a minus sign? Minus. Okay. It's got the probability of a representative 2-cup event like R intersect B. We're going to have to work that out in a minute. But who now can tell us how many pairs of cups there are? 6. So there are going to be 6 events like this, all with the same probability. Next one has a plus sign. And now we're going to have events of which a representative one is R intersect B intersect G. How many of these are there? 4, because we're leaving 1 cup out. And finally, we have to subtract off the probability of the one event R intersect B intersect G intersect Y. Okay, let's finish this up and we can take our break. What's the probability that the red cup plops down on the red saucer? 1/4. What's the probability that the red cup plops down on the red saucer and then the blue cup plops down on the blue saucer? So the red cup has already plopped down. It's 1/3 for the blue cup now to do this, and the probability of this intersection is, as was just said, 1/12. Okay. Now, R intersect B intersect G. We got 1 chance in 12 of getting the red and blue, right? Now I walk over with the green and plop it down on one or the other of these 2 saucers. What's the chance that I hit the green saucer? 1/2. And finally, what's the probability that I get all 4 right? 1/24. So, with a common denominator of 24, I have 24 24ths minus 12 24ths plus 8 24ths minus 1 24th. Didn't come out right. What did I do? Oh, that should be 1/24th. Good thing I knew what the answer was. Okay, that's 12, 16, 15 24ths, or 5/8. And I don't know of any intuitive way of getting the answer to this question. This is a case where inclusion-exclusion is the best known method. Now, how many of you have studied elementary Taylor series? Okay, a few, so I can't resist this. If I write this out, I have 1 minus 1/2 plus 1/6 minus 1/24. And there we stopped, but the temptation is irresistible to do that. So here's an interesting question. Suppose I start with a very large number of cups and a very large number of saucers. By obvious extension of this, though I haven't actually proved this, I would end up doing this sort of summation. Does anyone know what that series sums to? Jerry?
It's 1 minus 1 over E.
It's not, there's no 1 minus, is it? It's just 1 over E.
1 over E.
In other words, if you take the Taylor expansion of the exponential function and substitute in -1 for x, you get this series.
I've already worked this one out. You got it. It's the series for 1 over E begins with 1
Oh,
minus
sorry,
1.
sorry, you are right. The probability of getting none of them is 1 over E, and this is 1 minus 1 over E, because the series for 1 over E starts with an extra 1 on it. Thank you. So this is a famous problem that we'll come back to later. Question? Oh, well, we're done. No, I may have 5 minutes left, but this is the right place to take a break. So let's take a few minutes off. If you haven't dropped off your homework, please do it. And we will resume with breeding hamsters and family planning. Okay, so the next problem I want to do is from the example in the book that is called Urns. But I'm going to do an example with pet shops and hamsters. When I was writing the description for this course, I tried doing a little bit of marketing. You notice the applications to historical research and national security and so on. And with this one, I could have said to population biology and animal husbandry. So we'll do the Urns simulation, but talk about it in terms of hamsters. So somewhere around here, I have my simulated urn, yes, my Baltic cruising tote bag. And into this, I am going to dump 3 yellow cards, which represent male hamsters, and 3 purple cards, which represent female hamsters. And I'm going to shuffle them all up. And the orthodox way of doing this is to talk about putting balls into an urn and pulling them out. So, you go to the store with your kid, and you have not only been foolish enough, as I once was, to offer your kid 1 hamster, you've been foolish enough to offer your kid 2 hamsters, chosen at random. And so the kid reaches into the cage and pulls one out, and out comes a nice little boy. Now the kid reaches in, and you think, uh-oh, if the next one that comes out is a girl, we aren't going to have 2 hamsters. We're going to have 2 to the nth hamsters before wrong. And you hold your breath, and out it comes, and, oh, it's a girl, lucky you. So the question is, what's the probability that that will happen? And this is a nice, simple example where the most obvious guesses for the equally likely alternatives are wrong, though it's not hard to figure out the right one. So you can say there are 3 outcomes. Male, male, female, female, and male, female. And those are certainly not equally likely. So I hope you get the general message that in general, you can't just enumerate the outcomes and say, and now I'm going to assume they're all equally likely. You have to have a basis for that belief. Last week we had a basis for it with the dice. We had a basis for it with the roulette wheel, and so on. And these are not equally likely. And a slightly less silly alternative is also not right. You might say, the problem is the boy and the girl could come out in equal order, in either order, but those are also not equally likely in this particular case. If you were tossing a coin twice, the four outcomes, head, head, tail, head, and head, tail, would be equally likely, but not in this case. And it would take only a subtle change in the experiment to make it equally likely. If I change the experiment to this, pull one out, put it back, let them run around a bit, and pull another one out, for that which is sometimes called sampling with replacement, these four are equally likely, and that's an easier problem than the one that I'm about to solve. That is also, however, not what you want to do if you're getting your kid two hamsters. If you promise your kid two hamsters and say, pick a hamster out, we'll put it back, put a hamster out, oh, you only get one hamster because you pulled the same one twice, you're going to have one angry kid on your hands. So we've got to solve this problem exactly, and the outcomes that are equally likely are all ordered pairs of hamsters are equally likely. That is, if you number the hamsters 1 through 6, the probability that first you'll get hamster 3 and then you'll get hamster 5 is the same as the probability that you'll pull number 2 followed by number 1. So all ordered pairs, like, for example, 3, 4, are equally likely. Now, we're going to start with n males and n females. So how many ordered pairs are there? How many choices are there for the first hamster your kid pulls out of the cage? 2n. Okay, now you're holding on to this wriggling hamster. Your kid reaches in to pull out a second one. How many choices are there for the second one? 2n minus 1. Okay, and each ordered pair of hamsters is equally likely. Now, let's think about the ordered pairs that contribute to the event your kid is interested in, namely getting a breeding pair. So let's count the number of breeding pairs. Any of the 2n hamsters will get you off to a good start, won't it? But once your kid has selected the first hamster, how many hamsters of the opposite sex remain in the cage? N. Okay, so now we can use our general principle. In a simple case like this, to calculate the probability of an event, namely the pair of hamsters you get is a breeding pair, you divide the number of ways that the event can show up by the number of elementary outcomes, and the probability of getting a breeding pair is simply 2n times n over 2n times 2n minus 1, which is n over 2n minus 1, which is a little bit greater than 1/2. And once you see the answer, you see a much simpler explanation, namely, okay, kid, pick a hamster, any hamster. You got it. Now reach into the cage. There are 2n minus 1 hamsters left. N of them will give us a breeding pair, and n minus 1 of them will give us hamsters that can only get married in Massachusetts. So that's an easier explanation of the same phenomenon. It's a simplification of the counting argument. Any questions about this one? Okay, now the next one is really nice. This is another example from the textbook, and one of the things I like best about this textbook is that Sturzaker really has a nice collection of instructive examples and does a good job of pointing out the general principles that they illustrate. This is a very good one because it's easy to enumerate the outcomes and a little bit tricky, unless you're systematic, to work in terms of equally likely outcomes. So we're moving on to number 7 now, which is called in the book family planning. So here's the idea. A couple decides they're going to have a modest number of children, and we're going to assume that with each birth, you've got a 50% chance of getting a boy and a 50% chance of getting a girl, and we're interested in things like the probability that there's exactly one boy in the family, the probability that there are more girls than boys, more boys than girls, and so on. And I want to start with the easy case. But before I do, let me say a little bit more generally about this. So the peril I'm trying to teach you to avoid is mistakenly assuming that each of a set of individual outcomes is equally likely. And a good way of avoiding that is to start with a bigger sample space. In this case, it's going to be fictitious in a couple of the special cases we deal with. Start with a bigger sample space in which you can assume the individual outcomes are equally likely. And an example that you've already seen of this. You got 2 dice. The total can be 2, 3, on up through 12. And those are not equally likely. However, if we want to calculate the probability of rolling a 6 on 2 dice, say, we can start with a set of outcomes that are equally likely. If I roll 2 dice like this, no need really to put this on camera. What's the set of individual outcomes that, oh, that was quick work. What's the set of individual outcomes that are equally likely?
Odd or even.
All the ordered pairs.
All the ordered pairs again. The number on the first die, the number on the second die. The probability of getting a 3 and a 4 is plausibly the same as the probability of getting a 1 and a 6 or a 2 and a 2 and so on. So if we look at pairs like 1, 1, 1, 2 on up through 6, 6, those are equally likely. So that's a familiar example of this approach. Now let's apply it to families, and here is the simple case. The strategy is have 3 kids and stop. And the outcomes are, of course, boy, girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. And these are equally likely. So it's very easy to answer questions about this situation. The probability of having exactly one boy in this family is what? 3 and 8. Simply because if you look through these individual outcomes, 3 of them have the probability. 3 of them have the property that there's one boy in the family, 3 out of 8. The probability of more girls than boys is what? 1/2. Because in 4 of the 8 cases, there are 2 or 3 girls. So this is the easy case, but it leads us into the more interesting case. So that was scheme 1. Oh. Or, yeah. Okay, so that was the simple case, which I think the book calls scheme 1. Scheme 2 is a little bit more interesting. Stop after 3 kids or 1 girl. The mother might, for example, believe that daughters are going to fight with one another, and she doesn't want that in her house, so she decides the minute we have a girl, we're going to quit. We can't afford to run the risk of having 2 girls squabbling all the time. Now this becomes a little bit more interesting because there are fewer families that can occur. You can have boy, boy, girl, boy, 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 girl, or girl, and those are not equally likely. So what I'm going to do is approach this precisely as the book suggests. Let's assume that this family is feeling generous and they say, well, look, there are other childless couples around. Tell you what, we'll have 3 kids, but after we have 1 girl, we'll put all the rest up for adoption. Okay? That will certainly produce the same probabilities of the family they keep. But now we can use the 8 equally likely individual outcomes, and all we have to do is put parentheses around the kids that get adopted. After a girl has been born, all the remaining kids get put up for adoption. So now we have only 4 outcomes. Here's one outcome, boy, boy, boy. Here's another outcome, boy, boy, girl. Here's a third outcome, boy, girl. And here's a 4th outcome, just a girl. And we can assign probabilities to these by counting. What's the probability that the family consists of 3 boys? 1/8. The probability that it's boy, boy, girl? 1/8. The probability that it's boy, girl? 2/8. Because this can arise in 2 different ways where you put a boy or a girl up for adoption, and the probability that the family consists of an only child who's a girl? 1/2. So you see how expanding the sample space, and you might want to change the storyline to go with this to make it crystal clear you've got it right, lets you get the correct answer to this sort of thing. Jerry, you have a question?
By multiplying together the individual probabilities of each event, too.
Yes, this is not the only way of doing it. I'm exhibiting one strategy, but you're quite right. Your suggestion is, well, first we can say there's 1 chance in 2 that the first child is a girl. After that, it must have been a boy, so there's 1 chance in 2 that the second one is a girl. That gives us 1/4. If that doesn't happen, we start with 2 boys and we get these 1/8. So yeah, this is another cat that can be skinned in many ways. If we look at this case, the probability of 1 boy becomes you tell me. What's the probability that the family has only exactly 1 boy in this case? 2/8, 1/4, yeah. So in this case, the probability of event 1 boy is 1/4, and the probability of more girls is? Again, 1/2. Interestingly, it hasn't gone up. But the probability of more boys in the family is 1/4, because only these two outcomes contribute to that. Okay, now I will do the last case. I think. Guess I'm going to have to see it. This, I believe, is the strategy that my mother used. So this is scheme 3. Stop after 3 kids or 1 of each. In other words, we'll have 2 kids. If we end up with a boy and a girl, that's our family. If they're both of the same sex, we'll have a third and try for something different. My mother tried and ended up with 3 boys, but, well, we calculate the probability of that. Okay, so now we'll go back again to the individual outcomes. We can expand the sample space and change the storyline by saying, if we get a boy and a girl, we'll have a third child and put him or her up for adoption. And I will look at the possible outcomes here. And I think in order to save time and board space, I will just mark this up in black rather than in green. So this is the same, this is the same, this is the same, this is the same, but in this case we'll have girl, boy, and put up the boy for adoption. In this case we'll have girl, boy, and put up the girl for adoption. This will stay the same as in the first case, and this will stay the same. So, in scheme 3, what are the possible outcomes? Well, we can get 3 boys. We can get boy, boy, girl. We can get boy, girl. And we can get girl, girl, boy, and girl, girl, girl. What's the probability of this?
You left out girl, boy.
I left out, no, that's really boy, girl. We're looking at the family makeup and we don't care which of the children is the older. So I will lump BG and GB together. So each of these has a probability of 1/8. And this has a probability of 4/8. And because before someone says to me, oh, there's another way of figuring that out, I'll say it first. Of course, you have a first child. Whether it's a boy or a girl, the probability the second one is of the opposite sex and you stop is 1/2. If that doesn't happen, then you either start with 2 boys or 2 girls, and these 4 family makeups each have a probability of 1/8. And that ends the finite stuff for tonight. So now we're going to go to infinite case, and I have to do one little bit of what I hope will be review, but my hunch is it's review of the result, and you probably saw the proof, but you forgot it. So this is topic number 8 now, sum of a geometric series. And for quite a while, this will be the only infinite series that you will need, and it will solve a whole lot of interesting problems. So here's the result. 1 plus x squared plus ... And I'm going to do the finite case first. So we sum this up through the term x to the n. And what I want to do is prove that that's 1 minus x to the n plus 1 over 1 minus x, as long as x is different from 1. And I am, of course, going to prove this by induction. So I need a base case. I'll use n equals 1. I could probably have used n equals 0, but I prefer n equals 1, where it says 1 plus x equals 1 minus x squared over 1 minus x.
And that checks by elementary algebra. And now I have to do my inductive step. And in this case, I am going to go from n minus 1 to n. For the purely technical reason, there's already an n plus 1 sitting in the formula, and I'd rather be dealing with n and n plus 1 than with n plus 1 and n plus 2. It would work perfectly well going from n to n plus 1, but I will choose to say I want to look at 1 plus x squared plus terms on up through x to the n minus 1 plus x to the n. And I've already stuck in the extra parentheses that let me treat this as basically the sum of two terms. Because since I'm doing an inductive proof, I'm now entitled to assume that the formula that I'm trying to prove for the case n is valid for the case n minus 1, and therefore I can replace this by what? 1 minus x to the n over 1 minus x, and then I have to add on x. That's an equal sign, yes. And what I have to add on is x to the nth, which I'm going to multiply by 1 minus x over 1 minus x. So when I do that, my common denominator is 1 minus x, and I get 1 minus x to the n plus x to the n minus x to the n plus 1. Those two terms cancel. And I've shown that the n case follows from the n minus 1 case. Now, you'll notice this is all finite, okay?
I'm not quite following the proof. It seems like in the inductive step, you're kind of taking for granted or just assuming what you're trying to prove in the first thing, where you're just saying the series up to x n minus 1.
But that's how induction works. I'm saying I'm assuming the truth of it for n minus 1 to prove the truth for n. And that's why this is a bit hard to catch on. At first it looks like circular reasoning, but it isn't, because you're always moving up a step. And once you have this, you can say, okay, knowing that result, that means since I know it's true for 2, it's true for 3. Now I know it's true for 3, so it's true for 4. And if I do it that way, I have to do it step by step by step. Now, I haven't told my Raoul Bott story about induction. Well, Raoul Bott is one of the famous, all-time famous Harvard mathematicians, and I had the pleasure of teaching a freshman linear algebra course with him, and he was doing this rather difficult proof that basis is well defined in linear algebra, which has to be done by induction. And so he started out by pointing out that it was obviously true for n equals 1. And then he went from n equals 1 to n equals 2. And then in a very similar way, he went from n equals 2 to n equals 3. And he said, well, I've done this twice, and I'm bored, so it's true in general. And that's called proof by induction. I thought, how clever. That's exactly right. Because if you start working 2 to 3, 3 to 4, 4 to 5, and you see you're doing the same thing every time, then you say, okay, I'm going to prove going to the next step in general, and that relieves my boredom because I only have to do it once. Well, what did I know? I went to grade the midterms, and we asked the students to prove something by induction. And one student wrote n equals 1, extended it to n equals 2. N equals 2, extended it to n equals 3. I'm bored, QED. So it's the right general idea, but you should do it formally. Now, this is still not an infinite series. So what I want to do now is I'm going to assume that x is between minus 1 and 1, that the absolute value of x is less than 1. Then, using some terminology that many of you have probably seen, the limit as n approaches infinity of x to the n plus 1, the annoying term here is what? If you take a number smaller than 1 and raise it to a great big power, what do you get? Something very, very small. And this limit is 0, which means that if you ask me to make it less than 1 trillionth, I can pick some exponent n so that x to the n plus 1 is less than 1 trillionth in magnitude. So that means I could take the limit of this, and the limit looks simpler because there's no last term. I just write a lot of dots here. And I replace this term by its limit, which is 0. And there's a formula that you almost certainly saw in high school. And you probably saw a sort of phony proof with dots where you multiplied through both sides by 1 minus x. That's got the spirit of the proof, but it's not as clean as this inductive proof. Okay, now we can go on to topic number 9, which is Sheherezade in the 21st century. Remember the Afghan warlord General Dostum back in the days when Afghanistan rather than Iraq was in the news? Well, let's just imagine that he captures a young lady named Bernoulli. You know, these Afghans frequently have only one name. And this Bernoulli, named after the person who first formulated this idea, is a very good storyteller. So Dostum says, I'm going to turn you over to the CIA. She says, wait a minute, I'm a great storyteller. I can tell you funny stories. Let's make a deal. I'll tell you a story every day, and if it makes you laugh, I get to stick around another day. The first day I tell a story that doesn't make you laugh, you can turn me over to the CIA. So this is Sheherezade with probabilities attached. And let's define some events. So A sub k is the event that General Dostum laughs at story k. And the assumption that I'm going to make about this is that the probability of this event, which I'm going to symbolize by Q, is equal to 4/5. And the complement of that event is that Dostum does not laugh. And the probability of that, which I'm going to symbolize by P, is of course 1/5. Okay, in the outline I have listed a bunch of events for which it's easy to calculate the probability, and since I don't really have enough space on the board to write these out, you might want to have outline page 5, number 9 in front of you while looking at this. First question, what's the probability that she's turned over to the CIA after telling precisely 3 stories? So this is case A, and strictly speaking, this is the probability of the event A1. On the first day, she tells a story that makes him laugh. Intersect A2. Second day, she does the same thing. On the third day, she tells a clunker, and she finds herself chatting with Donald Rumsfeld. Okay? The probability of this event is, of course, Q squared for the 2 funny stories times P for the 1 unfunny story. Fair enough? What's the probability that she's turned over to the CIA on or before the third day? Now, what I'm building up to is a proof that eventually the CIA is going to get it. But we'll work up to this from the finite case. So on or before the third day. And this event really looks kind of messy. She tells an unfunny story on the first day, union with funny story followed by unfunny story on the second day, union with funny, funny, unfunny. And we can work this one out too. The probability of telling an unfunny story on the first day is P. Funny, unfunny is QP. Funny, funny, unfunny is Q squared P. And we have a nice formula for this. This is P times 1 plus q squared, which is p times 1 minus q cubed over 1 minus q. But 1 minus q is the same thing as p, because they sum to 1, so that cancels that. And we get 1 minus q cubed, or 1 minus 4/5 cubed. Now, who can see a much easier way of getting that result? This is a DeMorgan's law type reason. What I've concluded here is the probability that the CIA will get her, at least by the third day, is 1 minus 4/5 cubed. What does that imply about the probability that the CIA will not get her within the first 3 days?
1 minus.
1 minus that.
It's 1 minus that, or 4/5 cubed. And that's obvious, isn't it? Because she just has to tell 3 funny stories, and the probability of that is 4/5 cubed. Okay, now we can do, let's skip right ahead to D. So D is find the probability that she's turned over to the CIA after telling K or fewer stories. And I'm not even going to write out what that event is, because we have more and more terms like this, but the answer is very easy to see. It's P plus QP plus Q squared P, and the very last term is Q to the K minus 1 P. That's the case where she's turned over after telling precisely K stories, the first K minus 1 of which are funny. So this is P times 1 plus Q plus on up through Q to the K minus 1. And that's P times, someone give me numerator and denominator for this.
1 plus q to the k
1, what Q to the K?
plus q to the k. 1 minus
1 minus Q to the K over 1 minus Q, but P is equal to 1 minus Q, so this is just 1 minus Q to the K. Again, simpler reasoning. She can avoid being turned over to the CIA for K days by simply telling K funny stories in a row. That has a probability of Q to the K. Okay. Now how do you calculate the probability that she is eventually turned over to the CIA? Note that that probability is the probability of an infinite union of increasingly messy events. Nonetheless, the answer is very easy. What do I do in this formula with K?
Let it go to
I let it go to infinity. And the probability that she's eventually turned over is 1. So there's the simplest example I can think of a mildly realistic problem which involves an infinite union of events, which is easy to solve just by summing a geometric series. Now I've got 2 more to finish up with. An easy one, which is craps, and a really nasty one, which is Achilles rolls a 6. So let's do craps first. Of course, all the world's craps players are well known to be skilled mathematicians who deal comfortably with infinite unions of events and who are good at summing infinite series in their head, because you can't play craps unless you understand these concepts. Here's why. To remind you how craps works, you roll the dice, hey, 7, I win. Oh, wow. Wow, I'm on a roll. Okay, but let's imagine that at some point
Here's a 3 on this die. I roll a 4. Okay. Now the game proceeds as follows. I keep rolling until I either roll a 4 or roll a 7. If I roll a 4, I win. If I roll a 7, I lose. And this involves an infinite union of events. Because in principle, I could do a Rosencrantz and Guildenstern and go for 1,000,000 rolls, rolling nothing but numbers other than 4 and 7. So there's no guarantee that a game of craps will end in a finite amount of time. And in order to calculate the probability of winning, once I have started with a 4, I need to deal with an infinite union of events. Now, I got the answer to this problem last week by setting up an equation. Frequently, in these infinite union cases, if you set up an equation and solve it, you get the answer very quickly. But I want to do it the hard way tonight by summing the series. So the probability of rolling a 4 is the number of ways of rolling a 4 divided by the 36 individual outcomes, or 1/12. The probability of rolling a 7 is the number of ways of rolling a 7 over 36, or 1/6. And the probability Q of rolling something other than a 4 or a 7 is 1 minus a 12 minus a 6, which is equal to 3/4. Now we can calculate the probability of winning. Because having established this point of 4, the nicest thing that could happen would be I immediately roll another 4. So the probability of winning after a point is 4. Strictly speaking, this is a conditional probability, but I haven't talked about that yet. So the probability of winning when I have to make a point of 4 is the sum of an infinite number of terms. The first way I can win is by immediately rolling a 4. The next way I can win is by rolling something that's neither a 4 nor a 7, and then rolling a 4. The next alternative for winning is twice I roll something that's neither a 4 nor a 7, and then I roll a 4. And there are an infinite number of terms, each of which is the probability of one of this infinite number of events in a disjoint union, which is the event that I win. Everyone comfortable with this? That is a piece of cake. It's P4 times 1 plus Q squared plus dot, dot, dot. This is P4 over 1 minus Q. P4 is equal to 1/12. 1 minus Q is equal to 1/4. And the answer is 1/3. Which is obvious. I would say most people, if forced to guess, would guess this. They'd say, sure, the answer is it's the probability of rolling a 4 divided by the probability of rolling either a 4 or a 7, because the rest just don't count. Okay, that's the easy case. Now, for the last one, I need 3 people who sign waiver forms, because I want you to come up here and play this game. Okay, I need someone to represent Achilles. So you're Achilles. And I need someone to play Briseis. Now, I saw the Troy movie. Briseis is good-looking but unhappy at having been told out of Troy. Anna, will you be Briseis? And then my Iliad's kind of weak. C is Chryseis. I don't know. I don't even know whether Chryseis is male or female. Does anyone know?
Who's male?
Okay, good. It's you. Come on up here.
He murdered Alexander's son.
Okay, so these folks play a little game of dice. And Achilles, you go first. You roll a die. Now, the deal is, whenever you get a 6, you have to drop out. Okay, Briseis, you go second. You're still in the game. Chryseis, you roll. Okay, so you drop out. Okay, now Achilles, you roll again. You're still in. Briseis.
Okay. And so you're the one surviving player. The probability of that is one of the homework problems. So if you saw the movie Troy, you will have noticed that Achilles and Briseis spent many nights in Achilles' tent playing dice. What we want to calculate is the probability that Achilles is the second person to drop out of the game, and the answer is 3,000 1,001sts. But it's actually not that hard a problem. Sturzacher makes it messier than it might have been by being so scrupulous about doing it just by counting. And the analysis that I'm going to do is entirely equivalent to Sturzacher's, only I'm going to pull everything out in terms of fractions, and instead of having lots of sixes multiplied together in the denominator, I'm going to multiply probabilities together, but I'll be doing exactly the same calculation and be getting exactly the same number in a slightly more conventional way. So here we go with the analysis of Achilles' rolls of 6, and I think I may have slipped up if the cameraman wasn't astute enough to figure out that I was onto this new topic a little while ago. So what I have to show is the probability that Achilles is the second to drop out. Is equal to 300 over 1,001. And I'm going to resist the temptation to say, if the answer is that messy, there's no way I can get it. Let's just go at it. Okay, now this is going to involve combining at least two tricks. One trick is going to be summing an infinite series to get the answer. The other trick is going to be enlarging the sample space. And in this case, instead of stopping after our first girl, we'll keep having children, put some of them up for adoption. We will say, in this case, Chryseis didn't have to sit down after rolling a 6. Chryseis could keep right on rolling. And so we're going to assume that if Achilles wins, on the R plus first roll, that we have R rolls both for Briseis and for Chryseis. One of them may have a 6, but kept playing the game just for fun. I'm going to use X to represent something other than a 6. So here are rolls 1 through R and R plus 1. And what we want to do is figure out all the individual outcomes where Achilles is the second player to drop out of the game, and this happens on roll R plus 1. Now, Achilles, if that happened to you, what must be your roll here? 6. And what about all your previous rolls? Not 6s. So Achilles has to have R X's followed by a 6 on the R plus first roll. Now, let's go for the case that actually occurred, which is the opposite of the one I put in the notes, where Briseis dropped out, where Briseis stayed in the game longer than Chryseis. So, if you haven't dropped out by this time, Briseis, what can you say about your rolls?
Well,
If you're still in the game, if you're the third player, there's no 6s. So Briseis has a whole bunch of X's. And for Chryseis, if Achilles on rolling this 6 is going to be the second person to drop out, Robert, what can you say about your rolls?
Fewer than R X's.
Yes, okay. Or another way of saying that, has at least one 6. Or not all X. So does everyone see
This characterizes an outcome in which Chryseis is the first to drop out, Achilles is the second to drop out, and Briseis is still in the game. So let's calculate the probability of such an outcome. And what we're really doing is figuring out the number of such outcomes that lead to Achilles being the second to drop out on roll R plus 1, and then dividing that by all the individual outcomes that can occur with R rolls for each of the three players and one more for Achilles. But I'm going to do it like this. For Achilles, what did you have to do? You had to roll an X R times and then roll a 6. Okay. So the probability that Achilles rolls will look like this is 5 6 to the R times 1 6. This is exactly like Bernoulli telling stories to General Dostum. Everyone comfortable with that? Okay, this one's really quite easy. Briseis has to roll nothing but X's, and the probability that she'll do that is 5 6 to the R. Everyone comfortable with that? And Chryseis isn't too hard. The minute I write down 1 minus, you'll see why. What's the probability that Chryseis will not do what Briseis did? That Chryseis will roll something that's not all X's. It's 1 minus 5 6 to the R. And the probability that Achilles will win on the R minus first roll is the probability of the intersection of these three events, right? It's Achilles does this, intersect Briseis does this, intersect Chryseis does this, plus one other term, namely the term where Briseis drops out first and Chryseis stays in the game. So I have to calculate the probability of this intersection and then double it. So I can say P Achilles drops out second on roll R plus 1 is equal to 2. That's to account for the fact that either Briseis or Chryseis could be the first person to drop out, times this 1 6 times this 5 6 raised to the 2R power. That takes that and that into account, times 1 minus 5 6 raised to the R power for Chryseis. So to repeat, going backwards. This is the probability that Chryseis will do what he has to. This is the probability that Achilles and Briseis will do what they have to. And this 2 takes into account that we've really got the union of two events, one where Briseis is the first to drop out and one where Chryseis is the first to drop out. So now we've got a formula for the probability that Achilles drops out second and does it precisely on roll R plus 1. How are we going to figure out the probability that Achilles drops out second?
The probability he drops out second on for each R.
Yeah, that's right. We have to sum the probabilities of his dropping out second for each R. So I'm going to have to erase this to stay above the line of the lectern. So the probability that A drops out second is equal to the sum from R equals 1 to infinity of 2 times 1/6, which is 1/3, times 5 6 to the 2R minus 5 6
to the 3R.
You've got this in your
Oh, I do.
that last hour should be extra.
Yes. Send me an email about that, if you will, Jerry, and I will fix the master and put it online. I'm doing this in tech, and if it's not what you see is what you get, and I slipped up in my proofreading. Yes?
A question, why are you summing from r equals 1 to infinity?
I'm summing from r equals 1 to infinity because if r equals 0, Achilles starts the game by rolling a 6, and he's the first to drop out.
Okay, so I was thinking r equals 1 would be Achilles. But okay.
Yeah. So the earliest Achilles can drop out second is on the second roll, and that's what we're calling r equals 1. Okay, I think we can sum this. So we've got 1/3 of the sum from r equals 1 to infinity of 5/6 to the 2r, which is 25/36 raised to the r power, minus the sum from r equals 1 to infinity of 5/6 cubed, which is 125/216 raised to the r power. Okay, we're almost there. 1/3. Now, this is a little bit tricky because it starts with r equals 1, whereas the standard geometric series starts with r equals 0. But if I take the standard series, which is 1 plus q squared plus ... and change it to q plus q squared plus q cubed plus ... one way of describing that operation is not that I do it by subtracting 1, but that I do it by multiplying by q. And if you think of it that way, it's very easy. So in the denominator, we have 1 minus 25/36. In the numerator, if it were the standard series, we just have a 1, but because the series starts at r equals 1, what have I got in the numerator?
No. 5/6.
Not quite 5/6. You're 25/36. Sure. Because to go from r equals 1 to infinity, I have to multiply the standard series by q, and here the q is 25/36. And then I have to subtract from this something where the denominator is 1 minus 125/216. And what have I got in the numerator in this case? 125/216. And this is arithmetic I can actually do. This is 1/3 times 25/11 minus 125/91. And now I can factor out a 25. This is 25/3 times 1/11 minus 5/91. Now, can I subtract two fractions before the tape runs out? This is 25/3 over common denominator of 11 times 91. 91 minus 5 times 11. That's 25/3 times 36 over 1001. 25 times 12 is 300. And lo and behold, I got the answer, 300 over 1001. So for next week, you can have the fun of calculating the probability that Achilles is the third rather than the second to drop out of the game. And of course, you should then work out the probability that Achilles is the first to drop out. That's very easy, and you can check your answers by making sure that if you add together the probability for Achilles to drop out first, second, and third, they sum to 1. Always a useful check when you're doing probability. And remember, if your book shows no signs of being here in time to do the homework, send me an email and I will send you the text of the problems assigned for next week that are from the textbook.